In this video, we simulate the fetching, decoding, and executing of an ALU instruction in the SCOTS CPU. For this purpose, we have built a simulation circuit in Circuitverse Simulator. This is the simulation part of the instruction code ALU instruction video of the How Computers Work Building SCOTS CPU YouTube playlist. The links to the playlist and to the circuit are in the description. Here we have built a simulation circuit to fetch, decode, and execute the ALU instruction. This circuit can do just this. It cannot run other kind of instructions. I put here just the hardware needed to run the ALU instruction. Let's see a quick overview of the circuit. Here we have the timing blocks, so the clock, generator, and the stepper. Here we use the timing blocks and the wires coming from the instruction register to give the enable and set pulses to the dedicated register as the temporary registers, the accumulator, the memory address register, the instruction address register, and the instruction registers. Here the logic to give the set and the enable pulses to the 4 register from R0 to R3. Here we have the instruction register and the logic to control the opcode for the ALU. Here the instruction address register. Here the RAM memory. Here the ALU, and these are the 4 registers of the SCOTS CPU from R0 to R3. Let's see more in detail the timing blocks, so the clock generator, which also generates clock enable and clock set and the stepper, which is composed by 6 steps, lasting a clock period each. SCOTS CPU uses this stepper to give the right sequence to all the operations the CPU has to do. Moreover, I introduce a block called stepper cycle to decide how many stepper cycles run. In this way, I can stop the simulation and see the result of the single instruction. SCOTS CPU operates an instruction per stepper cycle, so an instruction per 6 clock cycles. Of course, it is highly inefficient, but SCOTS CPU has been created for educational purpose. Here we see on the left the generation of the enable pulses to the instruction address register, to the RAM, and to the accumulator. On the right, we see the generation of the set pulses to the instruction address register, to the instruction register, to the memory address register, to the temporary register, and to the accumulator. The pulses are created through 2 input AND gates, having as first input the clock E or the clock S, and as second input the right step of the stepper, which makes sure the pulses are created at the right time. To understand the wire connections, see the proper simulation videos in the playlist, in particular the fetch simulation and the ALU instruction videos. Here you see the instruction register. In SCOTS CPU, the instruction has 8 bits. If the first bit is at 1, we have an ALU instruction. So, for example, this instruction says add the content of the register 1 to the content of the register 2 and write the result into register 2. So, from the second to the 4th bits, we have 3 bits opcode to choose one of the 8 operations the SCOTS ALU can perform. The 5th and 6th bits define the register from which we get the first operand of the ALU. We generically call it register A, which in this case is register 1. The 7th and the 8th bits are related to the register in which there is the second operand of the ALU, generically called register B, in this case register 2. The SCOTS ALU operates only with the 4 registers from R0 to R3. So we need 3 decoders 2 to 4 to manage the 4 registers. In the blue ring we see the decoder to select the register A. We only give an enable pulse to register A to put the byte on the bus. In the red rings, the 2 decoders for selecting register B. We give an enable pulse on the left and a set pulse on the right to acquire the result of the operation and store it in register B. The decoder selects the right register, but the right time for the pulses come from clock enable or clock set, along with the proper step. Here comes the step for the enable of reg B, and the step for the enable of reg A, and eventually the step for the set of reg B, which is the last step, in which we store the result of the ALU operation in a register. Here the logic to drive the opcode. We have three AND gates with three inputs. One of the input is connected with the first bit of the instruction register. If this is 1, it enables the AND gates. If it is 0, it puts the opcode to the value 000, selecting the header operation in the ALU, because in general we need the header even outside the ALU instruction, for example to increment the instruction address register. The second input of the AND gates is activated in the fifth step of the stepper, which is the time in which the SCOT CPU performs the ALU operations. The third input of the AND gates is dedicated to the opcode, such that the opcode passes unchanged from the instruction register to the output of the AND gates in the fifth step and only if the first bit is at 1, so if we have an ALU instruction. Here you see the instruction address register connected with the bus in red. The IAR contains the address of the next instruction stored in RAM. This register is updated in the first three steps of the stepper cycle to point always the next instruction. Here you see the four registers from R0 to R3, so our reg A and reg B selected by the last 4 bits of the instruction. Here you see the RAM having two inputs connected to the bus, one for the address, connected to the memory address register, and the other for the data. Here you see the ALU with two inputs connected to the bus. Input A is directly connected to the bus and input B is connected to an element called bus1, which puts the number 1 on the bus when we want to increment by 1 the instruction address register, operation we do every stepper cycle. Bus1 is then connected to the temporary register where we temporarily store one of the operand of the ALU while the other is on the bus. Eventually, we have the accumulator register where we store the result of the ALU operation before storing it into the selected register. So now we run the simulation in which we fetch, decode and execute an ALU instruction. So we go here and through this enabler we put a byte on the bus and we can acquire it inside our register. So first thing, we put on the bus the address of the instruction. So we put the instruction at the address 0. So we acquire in the RAM this address precisely in the memory address register, giving a set pulse. And we put the address of the instruction inside the instruction address register, giving a set pulse. So now the instruction address register contains the address 0, where we are going to put the instruction. So the instruction is an ALU instruction, so in the SCOT CPU we have to put the first bit at 1, and we can perform, for example, an addition, so we leave second, third, and fourth bit at 0, so the code is 000, so an addition. And we use as reg A the register 1 and as reg B the register 2, for example. So the instruction says to add the content of the register 1 to the content of register 2 and write the result in register 2. So now we put this instruction inside the RAM at the address 0. So here we put the byte on the bus and we acquire it at the address 0 because the memory address register selecting the register 0. So we just give a set pulse and we acquire the instruction. So let's see. If we give an enable pulse, we see this is the instruction at the register 0. Now we put the data inside the register. For example, we can put the number 6 and we can acquire it in register R1. Okay, and the number 3. Oh, sorry, the number 3, and we acquire it in the register 2. Okay. So at the end of the simulation, we expect that in register 2 we have the number 6 plus 3 equal 9. So we expect inside the register 2 the number 9, and we expect inside the instruction address register the address 1, because every cycle we have to increment the address where we will find the next instruction. So we go to run the simulation, and we use here our stepper cycle, where here I select the number of cycle I want to perform. In this case I want to run just one instruction, so I need just one cycle, so I put here the number 1. I give here reset pulse, and you see I perform one cycle of the stepper. So the simulation. Okay, so let's see inside register 2 what there is. We give an enable pulse to register 2, we put the byte on the bus, and we see the number 9. The first and the fourth is, so 8 plus 1 equals 9. So we free the bus, and we see inside the instruction address register what there is. We give a pulse, and there is the number 1. So everything has gone as we expected, because this circuit has fetched the instruction in the instruction address register. You see here the first bit is at 1, and the 4 and 5 is the number 1. This light green is a 1, and in dark green is the 0. So the 6th and 7th is the register B, and it is the second register. You see here we are selecting the register number 2, and here 2, because this is the enable of reg B, and this is a set of reg B, and we select the register 2 as the instruction says. For register A, we select the instruction number 1, and you see 0, 1, the 1 line is at high level, so it is at 1, and so you see here our instruction correctly. We have seen in the instruction address register the number 1, so this is been correctly updated, and inside register 2 we have found the result of the ALU operation, in our case an addition. So let's see the simulation of another ALU instruction. So first we put the address on the bus, we acquire it in the memory address register and in the instruction address register. So the address 0 always here. Then we choose the instruction. For example, we can perform an AND operation. So first bit is at 1 because it is an ALU instruction, and the code for the AND is 100. So 100, and we use as reg A the register 0, and for example as reg B the register 3. So we put this instruction on the bus. This instruction says basically put the content of register 0 in AND with the content with the register 3, and store the result in register 3. So this is our instruction. We put on the bus the instruction, and we acquire it in the cell 0. So now we are going to put into register 0 and register 3 some data. For example, we can have all bit in this way. Okay. The first 5th bit are at 1, and the last 3 at 0, and we put this into register R0. So set pulse. Okay, and into register 3 we can put this byte here, So the first 4 bits at 0 and the last 4 at 1. So all the bits are different and just the 5th bit is equal. So we are going to expect inside register 3 at the end of the operation 1 byte, all 0, but the 5th at 1. So I put this byte inside register 3. Okay, let's see, inside register 3 there is this, and inside register 0 there is this other byte. Okay, so let's go to run the simulation. Again, it's just one instruction, so I leave this at 1. I want just one cycle. I give a upset pulse and the cycle is performed. So I go down here and we see what there is inside the register 3. So every bit's at 0, but the 5th is at 1. So we performed an AND operation with the 2 byte I've already put in the register 0 and 3. So we free the bus, we see if the instruction address register has been updated. We put the content on the bus and this is updated to the address 1 where we should find the other instruction. We see here the instruction is inside our instruction register because you see in light green the 1 and in dark green the 0, and you see this is 11000011, which is the AND operation between register 0 and register 3. So you see as register B you select the third line, so register 3, here 2, and the first line because it's register 0, so we select register 0. Okay, it worked. Please leave me a comment, let me know if you liked this video, make sure you put a thumb up, click the notification bell and subscribe to my channel.